All right, so this is now the last bit then, and it ties up with, I can't remember which one of the assessment criteria it is, but the last one in Learning Outcome 1. So calculations, interpreting data from Born-Haber cycles, I think it is, relating to lattice enthalpy or something like that. So the topic is lattice enthalpy. Now you will also see it, well, you'll see a fairly interchangeable use at this level. You'll sometimes see it written lattice energy. Lattice energy is actually something different from what we're going to do. It's a different sort of calculation. It's more physics based, so you don't want to touch that. But lattice enthalpy, lattice energy are not dissimilar, but you can make comparisons between the two. And I will mention this when we get to the right point. Lattice enthalpy is calculated more through experimental data that people have collected over the years. Lattice energy is more theoretical. So there is that difference, and sometimes you need to be able to describe or explain, I should say, why there's a discrepancy between the two. And it's all down to the way that we imagine or model, if you like, ions. You know, what shape are they, for example, that sort of thing. Now, if we start off with some sort of definition of this, lattice enthalpy, I'm just going to call it LE for now. What it is, a lattice, if you think back to when, it was a long time ago, when we did ionic bonding and we had sodium chloride, do you vaguely remember sodium chloride existing as a crystal lattice? That you'd got, for every sodium you'd got 6 chloride ions around it, and every chloride had 6 sodiums around it. And all the ionic compounds will tend to form this lattice structure. So that's what this is about. And it's about the forces between the ions that you've got in a solid crystal lattice. And you can look at it sort of from 2 different angles. You can either look at lattice enthalpy being the energy that's required to blast a solid lattice into its component ions in gaseous form, separated as far apart as possible, or you can look at it as the energy that's released when 2 ions come together from indescribable distances to actually create the crystal lattice. So there's actually 2 sides to it. Not surprisingly, one of those measures would be exothermic, the other would be endothermic. But generally, just the term lattice enthalpy on its own doesn't actually define that, so I'm going to add other words in, but then we'll make some assumptions as we go along. So really it's about the strength of forces between ions in a solid. So obviously the greater the lattice enthalpy, the stronger the forces. Okay, that sort of hopefully goes without saying. I don't think I need to write that down. Now, you'll only completely break those forces then if the ions are gaseous and they're so far apart there is no degree of attraction between them. All right, because you've got to break all the forces. So it's a rather strange idea, and a lot of this, although I say it's experimental numbers that we use, there is a distinct overlap with the theory and the theoretical sort of ideas that give you other calculations. So these forces then only completely broken. If you can break a force, I'm not sure that's quite the right sort of English. So the forces are only completely broken, but hopefully you know what I mean in that sense. When the ions are present in gaseous form, and that's always quite hard to imagine with, something like, say, a lump of sodium or magnesium or iron or something like that. Imagining a gaseous form of a metal is quite extreme. So in gaseous form, let's say so far apart. So this is part of the assumptions that we make. So far apart, there is, I'll put negligible, all right, so much you can ignore it, negligible attraction between them. All right, now just putting this simply in terms of an energy diagram, because we've used these before with the, just the vertical sort of scale. If we were looking at a enthalpy increasing up the board, because that makes sense, then our lowest energy, I'm going to use sodium chloride, by the way. It's the most obvious one to start building from. The most stable state for sodium chloride is not as gaseous ions separated far apart, is it? If you think about it, it's as a solid. That is a nice stable arrangement of particles. So our lowest energy form of sodium chloride is down here. So this is our solid. And then at the higher energy state, we've got sodium ions in gaseous form. A bit scary imagining those. And chloride ions also in gaseous form. So, in terms of the change between these two, you can convert between them. I'll do a two-way arrow actually, just to make it clear it's a two-way process. That this could be plus or minus, depending which way we're going. We'll work this out in a minute. 787 kilojoules per mole. Make that assumption with all the enthalpy stuff, we're using the same units. Okay. So, which way's which? If we were to go from the ions to the solid, what's that going to be, positive or negative? Sorry? That's negative. Yeah, we're coming down. It's from here to here. Coming down is going to be the negative one, isn't it? It's essentially a formation of bonds between them. And just think about bond enthalpy. So when we did that, you've got to put energy in. It's endothermic when you break them apart, and it's exothermic when you form bonds. So if we come down, all right, the downward bit, let me use a couple of other colours on here to make it clear. That bit, all right, that's the formation part of it. And to distinguish between the two, we can call it lattice formation enthalpy, or enthalpy of lattice formation, doesn't really matter. So that's the negative one. So then it doesn't take much to work out that the one going up the board, increasing the energy content of the particles, well, that's our positive one. But this is where we are taking sodium chloride and blasting it apart into these ions that are so far separated there's no attraction between them. We call that lattice dissociation enthalpy, or enthalpy of lattice dissociation. Doesn't matter, the terminology's a little flexible. Dissociation enthalpy. And that's our positive one then. All right, and if you look at the way the arrows go, that's just telling you whether they're negative or positive. Coming down the board, it's going to be negative. Going up the board, it's positive. So hopefully, so far, that's reasonably straightforward. Now, these numbers are affected by two particular factors. So I'll go down that route next. What I'm likely to do with this is head off in one direction and then have to come back again, because I haven't in my mind got the sequencing perfect on this yet. So you will have it all together eventually, but not necessarily in the right order. All right, so we've got a sort of definition, and I think I might as well stay on this page actually. We'll move on then to the factors affecting lattice enthalpy. I'm just going to call it LE still for now. We could, I suppose, use delta H naught. You'll sometimes see an L, you'll sometimes see lat, but that would work for lattice enthalpy. All right, so it's a little L down there, but you can sometimes see LATT. It's just easier to write LE, to be honest. The first thing that affects how big these numbers are is the charge on the ions. All right, so if we did, as an example, sodium chloride versus magnesium oxide. All right, it's not who wins in a fight between. But the ions have different charges. Sodium chloride, what are the ions on sodium and chlorine? Sorry, what are the charges on a sodium? What's the charge on a sodium ion? 1 plus. Chlorine is 1 minus. Right. Magnesium is 2 plus. And oxide is 2 minus. So there's actually a much greater attraction between the ions in magnesium oxide because the charges are greater. Now, it's not going to be double or anything as magically simple as that. But if you've got the more charge difference, the more charge on individual ions you've got, the more attraction there's going to be between them. So other than that, sodium chloride and magnesium oxide arrange themselves pretty much the same in a crystal lattice. But you've got, with the sodium chloride being around about the 787 mark that we just had up there, in comparison, magnesium oxide's more like 3,900. So huge difference, all right? And that's because you've got this difference in the charge on the ions. So you've got same arrangement of ions, but sodium chloride equals the 787. And the magnesium oxide is, it's roughly, I didn't look it up exactly, I read it off a graph, right? So it was 3,900-ish. Shouldn't use the ish in chemistry. The ish is a biology unit, I think. However, it's only a matter of comparison here. We're looking at a huge difference, aren't we? So what you've got here, the sodium and the chlorine there, only 1 plus, I should have put 1 plus and 1 minus, whereas the magnesium, all right, you've got 2 plus, 2 minus. So here, the greater charge that you've got there, you're going to get this difference in attraction. So greater attraction between the 2 plus and the 2 minus. Obviously, you're going to have in-between cases as well. So you might have sodium oxide, where you've got 2 single charges on the sodium to cancel out the 2 negative charges on the oxide, or magnesium chloride, MgCl2, and that, you've got to sort of work out where you stand with those as you meet them. But I don't think you will. I think I'm going to keep it straightforward. Otherwise I shall confuse myself as well as you. So that's one of the factors. There is a second one. And the second one is the radius of the ions, how big they are. And this takes us way back, and it's not even something that we considered significantly when we were doing the periodic table and sizes. So this is sort of mostly new, to be honest. So the second thing then is the radius of the ions. And if you think about it, this sort of makes sense, because if the smaller they are, the closer packed they'll be, so the greater the attraction between them. Right? And the bigger they are, the looser they're going to be arranged, you know, the further away they are, sort of in terms of charges and things. All right, so let's start with our, right, okay, the sodium and the chloride and the magnesium and the oxide there. Which ones are going to be smaller ions, the sodium ions or the magnesium ions? The sodium and magnesium ions, if you look at them in the periodic table, they're on the same period, aren't they? Yeah, third row down, sodium and magnesium. All right. Now a sodium atom has how many outer electrons? 1. It loses that and becomes Na+. Yeah. Magnesium has how many outer electrons? 2. So it loses those and becomes Mg. 2+. Right. Okay. So in terms of electron numbers, is there a difference between them, the ions? No. They've both got the same number of electrons, which is 10. Yes. All right. They've got 2 in their first shell. They've got 8 in their second shell, but they've lost the odd ones they had in the third shell. All right. So there's no difference actually in terms of the number of shells they've got. But what is still different between them? The number of protons. Yeah. Which one has the most protons? The magnesium. Yeah. So that is going to exert a greater attraction on the remaining electrons. So it will pull them in more. So the magnesium ion is the smaller of the two. And as you go across the period, you get that pattern. All right, because you've got the increasing proton number to take account of, and its charge is going to be pulling on those electrons, so it pulls them in more. Similarly, the oxide ion is going to be smaller than the chloride ion. Does that make sense? Not so easily, does it? The chloride ion has gained 1 electron, the oxide ion has gained 2. They both end up with the full shells. And I'm going to be really stuck trying to explain the difference between them. Let me pause this and think about it. Much simpler than, yeah. So whereabouts is oxygen? Once it's got its 2 extra electrons to make full shells, how many full shells has it got? 2 full shells. It fills the second shell. Chlorine, on the other hand, when it gets its extra electron, has filled its third shell. So, of course, it's bigger, isn't it? All right. If I was comparing oxide and fluoride, I'd have more trouble, wouldn't I? And I think that's what I thought I was trying to do in my head. But you've got an additional shell with the chloride, so that's bigger. All right. So, the sodium ion is bigger than the magnesium ion, and that's just because you've got the same, although you've got the same number of shells of electrons, you've got a greater positive pull in the magnesium ion. And the chloride ion is bigger than the oxide ion because it's got an extra shell anyway. All right, so our smaller ones are the magnesium and the oxide ions, but for different reasons. You know, the sodium, it's about the pull of the protons. For the chloride, it's about the number of shells that we've got there. So the closer together they are, the greater the attraction you're going to have. And so if you were to sort of go across the periods or down the groups, you get patterns that you can actually see in those. So if you go, let's say we've already started with the sodium and magnesium, that the ions are getting smaller as you go across. What about if you go down? What if you went down a group? What's going to happen as you go down group 1 to the size of the ions? They're going to get more shells, so they're going to get bigger. Yeah, so the ions will get bigger as you go down a group. And if you went down the halides, the halogens, we've got, if you took, let's say, sodium, I'm going to confuse matters, but if you go down, there's going to be the same pattern as you go down the groups. But you've got to be able to make comparisons between positive ions, so the change in the radius of the positive ions separately from change in the radius of the negative ions. But think about increasing numbers of protons and increasing numbers of full shells. That's the, rather than trying to use examples. Radius is reduced by increasing number of protons or full shells. I think that pretty much explains what I was trying to do in that bit. Okay, so in magnesium oxide then, just keeping with these two for comparison, these are smaller ions. They're closer packing in the solid. So you've got a greater lattice enthalpy for magnesium oxide than you have for sodium chloride. Generally speaking, it'll lattice enthalpy will fall as you go down the periodic table. So if you were to compare, lithium chloride, sodium chloride, potassium chloride, the lattice enthalpy will fall because the metal ions are getting bigger. And if you go down the halogens, then sodium fluoride, sodium chloride, and so on, if you go down, again, the lattice enthalpy will fall, but this time because the negative ions are getting bigger. All right. Yeah. Danger of overcomplicating that. Right. So, how about calculations involving this? It's no harder, really, than the Hess's law stuff we've already done. And it's just a sort of specific application of Hess's law that can involve an awful lot more steps. When we've done the Hess's law ones, we've used perhaps 2 equations for your practical, but you've done it with 3, you've done it with 4. Did we have a 5? Or no, that was just in a dream, I think. But with lattice enthalpy calculations, we have a whole lot of intermediate stages that we can measure, because we can't actually measure lattice enthalpy directly. Now, the intermediate things that can be measured are some very strange enthalpy values that we've not come across all of them. We've met some of them, but these are quite separate from the bond enthalpies and the enthalpy of formation. This is a different bunch altogether. But once you get the hang of it, it is not very difficult. So, calculating lattice enthalpy. Alright, so the problem that we've got is that it's impossible to actually measure either of our situations, whether it's the formation or the dissociation of the lattice. So you can start off, you can have your solid crystal, and you can have your gaseous ions, you know, scattered as far apart as you can get them. And you've got that option or that option, and you can't measure either of them. So I'm not sure I've written that so it makes sense. Either that or that, right? So either of those, you know, you can't do it. You might think, why do you need to? I'm not entirely sure. I'm not a chemist. But there are a lot of uses for energy measurements in reactions that tell you a lot about the energy in particular atoms and ions and compounds that has other applications. But yeah, like I say, I am not a chemist and I don't actually want to know at the moment. As long as we can work it out, I'm happy with that. We've got these two ways of possibly measuring it, and we're going to take the usual route first, the experimental route that uses these things called Born-Haber cycles. I will explain about the theoretical bit when we get there. So the usual approach is to use these experimental values. So if it says, if you get a question that says experimental, this is the approach that it means. So as experimental values, using measurable enthalpy changes, because that one up there can't be measured. So what we want is to use some that we can, measurable enthalpy changes. And once we've got that, and we know about Hess's law, we're in with a chance, aren't we? So using measurable energy or enthalpy changes, and the bit about Hess's law that we need is these thermochemical cycles. See, I said you'd need them. And these thermochemical cycles are what we call Born-Haber cycles. All right, so yes, two people involved in that. I have no idea what either of them was specifically noted for. But Haber, you will come across a mention probably of the Haber cycle on the environmental biology unit when you meet the nitrogen cycle. Because one way of getting nitrogen out of the atmosphere and back into use in living organisms is to create ammonia for fertilizers. And the process that's used is called the Haber cycle. So, yeah. Chase the names if you want to, but yeah, time doesn't allow me to. For this, we need several bits of information. We are not actually going to do the experimental measurement for these because it involves things like atomizing sodium and then turning it into ions, and yeah, you can do that with the right equipment, but we're not doing it here. The information that you need, well, first of all, we need values for, well, I've got a bit of a list here. So first of all, one that we're familiar with, which is the standard enthalpy change of formation. All right, and you must have been thinking, isn't this similar? We're talking about elements here. Sodium's an element, chlorine's an element. Stick them together, you've got sodium chloride. Isn't that then the enthalpy of formation for sodium chloride? Yeah. Yes, but what's it made up of? There's all sorts of things. You can't just literally get a lump of sodium, some chlorine gas, and just hold them together and hope that some sort of magic will happen and you'll get sodium chloride. Sad, isn't it, really? So we can look that up in a book. That's one useful thing. So we know we can get enthalpy of formation. We then, however, need 3 other things, possibly more. Now, these 3 other things, first of all, standard enthalpy of atomization. Because if you've got a lump of sodium, it's bonded together with metallic bonding, isn't it? Or if you've got a molecule of chlorine, it's hanging around in diatomic molecules, Cl2. So we haven't got atoms. So first of all, you have an enthalpy of atomization to take into account. Once you've got your atoms, so you might have a sodium atom and a chlorine atom, that's a start, but you then need to turn them into ions. Now, for the sodium ion, we have met the idea of ionization energy, haven't we? If you remember in your very first assignment, you had to look at the trends in ionization energy and electronegativity. They're not the same, you know, they're not the reverse of each other, they are different. But there is a similarity between electronegativity and the next thing we need. But the ionization energy, for sodium, you only have to remove 1 electron, so it's first ionization energy. For magnesium, we would need first ionization energy and second ionization energy to get the second electron off. For the oxide from oxygen and the chloride from chlorine, we need something else. Now, this is not about bonding, so it's not about attracting electrons, so it's not electronegativity. But it's a similar concept. It's called electron affinity. And it means how strongly they will just pull odd electrons towards them. So you could have first electron affinity, which would be pulling 1 electron in to make a 1- ion, and then a second electron affinity, which would pull a second one in to make a 2- ion, like you've got for oxide. So these are all the components of the things that actually make up the enthalpy of formation. You know, there we were just thinking, it's, oh, you know, magnesium plus oxygen, and you've got magnesium oxide. No. You know, they won't just sort of spontaneously join together. We know there are energy changes for that one because you've done it. You might not remember doing it, but you burned some magnesium, didn't you? You had to keep lifting the lid on that little crucible. So we know there was a lot of energy involved in that process. But what was happening in the meantime? The stages in this are sort of theoretical. Whether they actually happen is, yeah, another matter. So I've got to go through these different values. I don't need to define that one I've just put up there, the enthalpy of formation, because we've already got that one. For the other ones, enthalpy of atomization I'll start with, that's fine. But when we get onto ionization and electron affinity, they're not always given the enthalpy symbols. But yeah, we'll get onto them in a minute. So once we've got that, we're on our way. The next thing we want is then standard enthalpy of atomization. And that, quite neatly, is one of these with an A. All right, so what this is, we'll give it a definition so you know where it fits when we're using it. This is the enthalpy change when 1 mole of gaseous atoms, what's that? It probably is, isn't it? Enthalpy. Enthalpy. It's because I'm trying to keep track of my notes so I don't wander off, not watching what I'm doing. And I'd only written nth in there anyway. Right, so enthalpy change when 1 mole of gaseous atoms, we're not ionizing yet, is formed from the element in its standard state. Now this is always going to be positive. You're always going to have to put energy in to get atoms out of the elements. Although I'm assuming you don't probably have any values for the noble gases, because that's how they are. They're already atoms, single atoms. So, you know, if we keep working with our sodium chloride, that would be sodium as a solid being converted into sodium atoms as a gas. So, yeah, it's not something I can even imagine. However, value for that, it's not that great. 107 even kilojoules per mole. Now with the chlorine, in order to get a chlorine atom, we have to say we're starting with half a molecule, but you know, you say to yourself, well, that is an atom anyway. But you also got to think of it on the scale of moles as well. These things don't necessarily represent atoms to start with. That is 1 mole of sodium as atoms, solid atoms. That's a mole of sodium as gaseous atoms. So this is half a mole of Cl2, right, which is, you know, I've put solid, I should have put gas, that's put standard state up there, sorry. Chlorine does not hang around as a solid. What we're going to get here is our chlorine just as a gaseous atom, and our enthalpy of atomization for that is 122 kilojoules per mole. So these are not huge values for atomizing those, but there's an awful lot of other things to add into the whole picture. Okay, so that's our enthalpy of atomization. I'm going to do ionization energies next, and then the electron affinities. The ionization energies, we can either express these, well, we'll start with the first ionization energy. You'll sometimes see that written just as first IE, or you might see it written as the enthalpy sort of version of that. I think it's just an I. I think I've got some handouts that have that version on a bit later on. Ionization. Oh, they've got, yeah, ion. All right. But you will see it most commonly just written as first IE. So we have met that before, and it's just you're taking a 1 mole of gaseous atoms, which of course we've just created up here, so you can see the direction this is going, I hope, into 1 mole of gaseous 1+ ions. All right, so for example, you know, substance X in gas form. Oops. It's going to lose an electron, isn't it? Pluses and minuses all over the place. Okay, so if that was sodium, it becomes sodium 1+, but equally it could be the first ionization for magnesium. All right, so magnesium, gaseous atoms, to Mg1+ would involve this amount of energy. However, we also have second, third, fourth, fifth, you know, increasing numbers of ionization energies. needless to say, you know, it's going to get quite hard. If you want to take a second electron off sodium, of course you have to then attack a full shell, don't you? So that is actually much harder. But for magnesium it's somewhat easier because it has 2 in its outer shell. So we'll put the second ionization energy in. You could have others, but this one, you know, is I might put it in brackets because you could have others as well, but you'd just be going from here, from gaseous 1+ ions to gaseous 2+ ions. All right, so in other words, it would be from our X+ that we've got there to X2+ and another electron. Okay, so it's a separate step. It's not 2 lots of that. It's not the only thing you do to remove 2 electrons. All right, it is the second of 2 steps if you are moving 2. And you could have a third ionization energy. You'd be unlikely to have a fourth, but I guess it depends what you're making. Now, this is then where we have to consider the other thing that I haven't mentioned previously, which is the first electron affinity. Now, this really is the other end of the periodic table, the other side, if you like. Again, you will often see it just as first EA, or you'll get I think what they've put on this sheet is EG, which is electron gain, but you might see EA. Usually they'll be defined, and you can usually work out what they mean anyway from where they are. So it might be EA, it might be EG. But electron affinity is what's happening over the right-hand side of the periodic table. So this is, again, per mole, as before. So if we've got 1 mole of gaseous atoms, this is going to our 1 mole of gaseous 1- ions. So this time I'll stick with, I'll better use a different letter, hadn't I? Let's use Y. So this time we would be adding an electron to it and getting our gaseous 1- ion over here. And then, not surprisingly, and I'll put this one in brackets again, we have a second, I'm not even going to give it its full name this time, right, second electron affinity or electron gain. This time you're going from your Y-, adding another electron, and ending up at Y2-. So, you know, if you're forming something like oxide ions, you'd have to go through the first electron affinity and the second. So when we do our calculation, we're going to keep it straightforward to start with and just do ones that are 1+ and 1-. And then we will take it from there. So how are we going to draw this out? Right, let's... I was going to just get you to draw this out roughly, and then I thought, no, I'll be kinder than that. Right. This is just to save drawing these things out. Just put some numbers on these. I thought a whole sheet of paper would make it easier because you can then sort of annotate as you go. So, yeah. I'm going to show you what this looks like. None of this will fit together really until we start to do this, so do not fear. This may well take me longer than today, but that doesn't matter too much. It does take a little while to... It will fit together once you've got this. I just want to show you what these look like once they're done. Here's a sodium chloride one. You take each of the steps that we've been looking at, the atomization, the ionization, the electron affinity, and you put it together on this. This is just an energy diagram, but it's a much more complex one than we've had before. So some of the energy changes will be positive, in which case we move up the diagram. Others will be negative, so we come down the diagram. And we are left with the lattice enthalpy, and we can then take a route around the diagram, like we could take different routes around those thermochemical cycles for Hess's law. This is exactly the same sort of process. All right? So that's what it's going to look like in the end, and then I'll give you some more examples, and the more of these you see, the more you'll get the hang of it. I don't want to use one straight off there. I want to actually build one, I think, although yeah, the temptation is to use this one, which is the Chem Guide one. It's got the numbers on that I want, so yeah, I might hide that on another page, perhaps. I'll do that. All right, I'm going to do, this one will be mine, so I'm going to put Bourne Harbour cycles on here. And then on the next page, I will put this one for reference, just in case everything goes horribly wrong. All right, so we can come back to that. Not that I don't trust myself, but you know how these things can work out. Okay, so we are going to build a Bourne Harbour cycle. This is the going to be to work out the lattice formation enthalpy. You could do the dissociation, but we're going to do it for the lattice formation for sodium chloride. Now, unfortunately, the sheet I've given you isn't a multi-purpose one for different substances. I actually scaled this so that it matched the, the relative amounts of energy that were going to be involved in this particular example. So others, you would, it's best done on lined paper or squared paper, so you've actually got a scale going up the page and you can see what you're doing. Okay, now our base point for this, and I wonder if this would be easier if I actually did it on the... I can open up Word, can't I? I can open up this particular... just trying to think where I've put it. Sensibly, it'll be in there. Bourne Harbour cycle for sodium chloride, blank. This will do the job. Except it's a bit on the large side. Let's just park that down there. Get that out of the way for now. No, because I can't make it smaller. I want it to, yeah, I couldn't zoom out easily. Right, oh, as good as it's going to get, isn't it? Oh, that's not too bad. Right, that will do nicely. Okay, where the heck do we start? Well, I'm going to start at the bottom. So I'll scroll it up a little bit so that... I would do if I could, but it won't let me. Down at the bottom, we've got our sodium chloride. Now, this is only going to let me write in black, isn't it? Unless I change it. So, down here, NaCl as a solid. That is the lowest energy form of any of the things that we're going to meet. Now, one piece of information that we can get, what can we look up in the book? The enthalpy change of formation. And so our next step up would be that, because this is a value that we know. And we form the sodium chloride from, and this is the standard state bits, from a mole of sodium chloride would come from a mole of sodium, solid sodium, and half a mole of Cl2. And that would be as a gas, because that's the standard state. And so we know that value, and the value is this change. All right, that's what we look up. You look up the standard enthalpy of formation for sodium chloride, and you will get the number -411. And I'm going to number the arrows as we go around in a minute, but this is our standard enthalpy change of formation. Whoops, I put a minus. That wasn't really supposed to be a... Hang on. That was it was a sort of indicator, but it's not really going to help. So we'll have our standard enthalpy change formation, and that is -411 kilojoules per mole. Are we all right just understanding that bit so far? Yeah? Because that's the bit we've done. Now, the next steps are going to involve things like the atomization and the ionization energies and electron affinities. So we're going to do the ones that will take us up the board first. And the next step would be to atomize our sodium. All right? We don't need to atomize the chlorine there. We're going to do that later on. All right? We'll deal with one thing at a time. So we can now move up to... I'm not going to have room for my arrows on here. You should have plenty of room. But I'm going from the solid that I had on the first line now to atomized sodium. That's in its gaseous form. All right, so we've got our chlorine in the same state. I'm not quite sure where I'm going to draw this. I'll have to put it here. And this then is our standard enthalpy of atomization for the sodium. Oh dear, the other one down the side's going to have to tuck itself away. And that is plus, well, you tell me, we've just written it down. Atomization for sodium, 107, yeah. Oh, and the units. Okay. The next thing is, having atomized our sodium, we then are going to turn it into ions. All right, and so that's our next step up here, and that's quite a significant input of energy. Whoops, that's my end point. Sorry, I put the plus in before. Actually, that, yeah, going from there up to there, that is what we end up with, turning it into that. All right, the gaseous sodium, which has lost its G. I don't like using ink on these, on the board like this, because you get this extra little dot that follows you around. All right, so we've gone from the sodium as a solid here to sodium as gaseous atoms here, to sodium as gaseous ions up there. And in order to get them into gaseous ions, you have to take the electron off. So that's what's happened to the sodium. At this point, nothing's happened to the chlorine. Right, it's still sitting there like that. And so we've got, not sure where I can stick the arrow for this one. Put it wherever is sensible. It should really, you should have them coming up in a line, but it's just not going to happen. This is a bit of an untidy Born-Haber cycle, just from the way I've had to fit it in. So this is our first ionization energy for the sodium. And that is an input of 496 kilojoules per mole. And then we can move on to the chlorine. Now we've sorted out the sodium. So our final upward step for putting energy in, up there, is going to atomize the chlorine. At the moment, we've got half a mole of Cl2 molecules. So what we're going to need up here is our sodium ions in gaseous form. They've got a loose electron hanging around with them. And then we've got a mole of chlorine atoms. All right, now you're thinking, well, how am I going to know all this? It follows the same pattern every time. You do them in the same sequence. All right, we just do 2 or 3 and you'll be, you know, got the same thing to do. So this is our delta H naught A, our enthalpy of atomization for the chlorine. And that's got a value of, we wrote this one down as well, didn't we? Plus 122. And I should have got rid of the units, I think, for this, just for ease of working it out. Right. The next step, well, we still haven't got all our ions yet. Okay. Now, up at the top there, we've got a sodium ion. We've got the electron that was pulled off it as we ionized it. And we've got a chlorine atom. Where does that loose electron end up? On the chlorine, yes. It attaches itself to the chlorine. So we've got our electron affinity of chlorine to consider next. Now, because that's creating a more stable arrangement, of course, that's going to start coming down the page. So from, oh, I need to write it in before I get in a mess, don't I? So there's our gaseous sodium ions plus our gaseous chlorine ions. Aha! Oh, now I've not, well, I'll have to put it down there, I'm afraid. Not ideal. But this is our first electron affinity for chlorine. And that's a value of -349 kilojoules per mole. And yeah, so wishing I'd not bothered with the units. So what are we left with? It's the final drop, isn't it? From those sodium and chloride ions down to the sodium chloride. So what would we call that? That is our lattice enthalpy. Yeah? Hopefully we're starting to now see, we could take various routes around this. All right, so that's your lattice formation enthalpy. If it went the other way, if I was going from bottom to top, it'd be dissociation. All right, but that is the thing we want to work out. Okay, now I'm going to just tag these changes with, I just want red. Okay. I'm going to call these, just give them numbers so they're easier to handle. We'll call this 1, we'll call this 2, 3, 4, 5, and then the final one, the one that we want to work out, is 6. So how can we work out 6 given the other bits? 6 goes from here to here. Now, we don't know it, but we know all the other stuff. Well, you sort of add them all together. You've got to look at which way they're going, haven't you? Not all of it, no, because they don't all go negative. The bottom one here, number 1, is already going in the right direction. So you wouldn't reverse that one. So now what we want to do is, let's see if this is why I've given you the big paper to do this on. And I'm not getting colour here. Let's try blue. Right, starting from here, then we want the negative version of this one, don't we? To get to there. Then we want, I haven't got room, negative version of that one, negative version of this one, negative version of this one, but we can leave that one as it is. Yeah? So we can take that route and we get the right value doing that. All right, so I'm going to let you try and work that out. Let's come up with a number and see what you get. Okay, minus 787 it is then. I'm going to save this as well, I'm not sure how else you would. Hang on a minute. If you do what? Minus this one, did you say? Well, that would imply that would be the dissociation if you went up one, wouldn't it? It would mean you were starting from NaCl solid if you started at the bottom. And you're supposed to be starting from the ions because you're calculating the lattice formation enthalpy. Yeah?
You get the same figure.
You will, because that's the lattice dissociation instead. So yeah, if we were doing this for, if I put lattice dissociation enthalpy, then we would have a different arrow. We would have, it would be this one, like that. Yeah? And in that case, yes, you would start with the sodium chloride down at the bottom here. You'd go up number one, and then, yeah, so you'd reverse that, but you'd keep all the others the right way round. So that would be starting at the solid crystal lattice, the NaCl, but ending up at the ions, the Na plus gaseous and the Cl minus gaseous. Yeah? So you're right to spot that, yes, you can go either way round it, but they are two different things. But that's this issue about, you know, saying lattice enthalpy on its own doesn't actually distinguish between the two, which is why, you know, saying lattice dissociation enthalpy or lattice formation enthalpy does just make that a little bit clearer. Right, I'm going to just put that down at the bottom for now, and actually I can come back. The one that we'd got, yeah, off Chem Guide, actually it's not very clear, the numbers, but those are the numbers that we've just calculated with. So actually I'm going to take that out of there, put it on here, and if on there, yeah, I can see it, but yeah, you probably can't. But if we numbered them again the same way as I did on that larger version. Ooh, have I lost one? No, that's that one, isn't it? And then that's 6. So if you're, oh sorry, I've actually put the wrong one on there, haven't I? That is the dissociation one, because it's got the arrow going upwards. Only just noticed when I got to that point. Remove that. Oh, okay. Right, forget that bit happened. But referring then to that, yeah, the sheet that you've got, yeah, so your overall number 6 is, yeah, minus number 5, minus number 4, minus number 3, minus number 2, plus number 1. So you know, you just get your starting point and end point right, and you're there. Okay, so on here I will put C separate sheet. Oops. Now, these ones then, this is very much about the experimental things that can be measured, although not entirely sure how. But it is just worth mentioning the theoretical versions of it. So theoretical rather than experimental values. All right, this is I've got a handout that's got several examples of cycles on, and 2 or 3 A-level questions to look at as well. So we will be back to that. The theoretical values, they make assumptions that aren't entirely valid in all cases. They are assumptions that you can actually evaluate in terms of the difference between theoretical and experimental values. You can then say, well, you know, this does apply or this doesn't apply in this case. The first assumption that's made is that the compound is fully ionic. Now, you've got to think back to bonding. Do you remember we talked about electronegativity differences, didn't we? And we started with the idea that if there wasn't much difference, you would have a covalent bond, a pure covalent bond. If the difference was slightly bigger, you'd have the polar covalent bond. And then if the difference was even bigger than that, then you'd end up with the electrons ripped off and a complete ionic bond. Well, it's not just, you know, start, stop with that. It's like a sliding scale, that you can have bonds which are mainly ionic but with some covalent character, that sort of approach. So you can actually make a comparison then between the theoretical and the experimental, you see, because theoretical assumes it's fully ionic. So if it doesn't match up, then it might be that that bond is not fully ionic, and that is something that, you know, can help you actually sort of see why these numbers are justified. The other thing that's a sort of slightly odd assumption is that the ions are really just point charges. Or I think the other thing is that they're sort of completely spherical, and that we know electrons are moving around them, and so they're not. But ions are seen as point charges with any charge that they've got concentrated at the center. And of course, if you've got electrons orbiting around the nucleus, sometimes they're all going to be over one side, or sometimes all over the other side, or they might be evenly distributed all around. Plus, of course, they're not two-dimensional, they are three-dimensional. So, you know, this again, it's a slightly dangerous assumption, but that's what's often done in physics. Theoretical physics is you have to, I mean, part of the science is about making the assumptions. You know, what assumptions can you make, and then what's wrong with that in other scenarios. Yeah, it is a bit like, yeah, any alternative sort of, yeah, it's not entirely true, but it's also, yeah, it influences outcomes. So what you get are, you end up with very complex calculations involved in this that we're not doing, you'll be pleased to know. Born-Haber cycle, that was straightforward as long as you got the numbers. You get two possible outcomes here. First of all, you get reasonable agreement between the theoretical and the experimental that you work out using a Born-Haber cycle. So theoretical and experimental. And what that means is that the assumptions are good for that particular compound. It's fine. However, you also get outcomes where there's a particular disagreement, and the one that's often quoted is silver chloride, or other silver compounds as well. So the experimental and theoretical, so exp and theo, don't agree. And yes, silver chloride, Al, just condensed it completely down into aluminium. AgCl. For that, the theoretical is a lot less than the Born Haber calculation would give you, and the theoretical less than experimental. And it's one of these things where you sometimes have to explain a difference. Why doesn't your experiment match up with what you predicted? And this is just a good example of how that can be done. This answer won't fit everything, of course. And the reason for this is because silver chloride is not actually entirely ionic. Now, from where it is on the periodic table, it's hard for you to understand this because it's a transition metal. If you look, it's over the right-hand side, second row down. All right. Now, the thing about silver is theoretically it could form all sorts of different ions in the middle there, but it loses one of a pair to become an Ag plus if it's going to be ionic, but it does have a significant amount of covalent bonding. And the reason for that, I don't suppose anybody's got their electronegativity table things with them, but there's not a huge difference between the electronegativity of silver and chlorine. There's not enough of a difference for it to be fully ionic, so there's a bit of covalent bonding, so there's a bit of sharing and a bit of transfer. So making the assumption it's 100% ionic is inaccurate, and that's what the value can actually tell you. So it helps you to work stuff out. So I need to explain that because silver chloride actually has a significant amount of covalent bonding. And the reason for that, not enough difference in electronegativities for complete transfer of an electron. So, it just really sort of shows us that it's useful to be able to make assumptions. And that's one thing, actually, I need to say about the assignment and the write-up of the practical on there. There are several assumptions that are made when you're doing calorimetry, which is what you were doing. And I haven't told you what they are, but it's something you should look into, right? That assumptions are made, right? And I guess with a lot of chemistry, you end up having to make assumptions. Right now, just to explain this in a little bit more detail, I hope. I've got a little PowerPoint that may or may not help. You never can tell, can you? But this idea of there being a scale of bond character, if you like, that there's a transition area where you just you can't say it's definitely one or definitely the other, that it's got some character of each, and what impact that has on the enthalpies. I've nicked somebody else's PowerPoint for this, so it's not that one. That's not that one. Transition from that one. eventually. Doesn't want to open up. Okay. Right. What you have then are these sort of options with bonds. It's not just covalent or ionic. We know about polar. So, you know, if you look at it on a scale like this, it makes sense, doesn't it? That, you know, the electrons are not just going to be in one place or another place. You know, they do spend their time moving about, or yeah, there's an area of electron density that, you know, you can find somewhere. So we have the pure covalent bond would be a perfect share, and that's only really going to happen where you've got two identical atoms. So, you know, two oxygen atoms in a molecule, two chlorine atoms in a molecule. You've got a pure covalent bond. We'll have the polar covalent bonds where we've got significant differences between the electronegativities, like we have between oxygen and hydrogen, and I mean that applies perfectly in water, but of course also in OH groups, which we find a lot of those in organic chemistry, but other examples as well. But you then have a bit of a transition area where you get ionic with covalent character. So although an electron's been transferred to the purple side there, and there is just about a sort of, you know, there is a sort of separation between the ions, the electron can't bear to leave home completely, and it's spending, you know, quite a bit of time in this area. So that's the covalent character. It's not been completely pulled away. And then you get your pure ionic. And it's these ones that we don't really sort of consider earlier on. But the others, we've met those. Now, the next bit, this idea of polarization, negative ions, positive ions, we have these rules, Fagen's rules. It's a long time since I've met these. I saw it and I thought, oh, that rings a bell. But it's this idea of the distortion, the negative ion becoming distorted and more covalent, and that's the polarized bit. So that was the, come on, go back. That was this third one down. You know, the idea here, this is, you know, pulled right over this side. So the extent to which that happens is going to cause it to have more covalent character. And we have these four rules here. So you'll get more covalent character if you've got a small positive ion, if it's got multiple charges, and this should be ringing a bell now from what we were saying earlier on about the lattice enthalpy. Also, if the negative ion's large and it's got multiple negative charges. Now, I don't particularly want to apply those directly, but we might come back to them. But it's just a matter of pulling electrons about. Now, if we make some comparisons between different compounds, then it's a little bit clearer to see. If we compare the chlorides, there are some differences here, and there's a trend in the degree of covalent character. All right, we've got sodium chloride up here, magnesium chloride here, aluminium chloride here. Aluminium chloride it describes it as quite large covalent character. In other words, this area here, there's a lot of potential sharing of the electrons in that. This is, you know, this is not, I mean, you'd have to have 3 chloride ions anyway for that, but ignore that fact. Because the aluminium's got a +3 charge and is quite small, again, it's because it's lost those electrons and you're left with these full shells. And so it's going to be quite polarizing. It's going to have a real sort of strong pull on the electrons that have potentially been transferred. And so if you have a look at the, you know, the difference between them, Na plus, you've got a good separation. Mg2 plus, slightly polarizing, you know, pulling the electrons over. Al3 plus, definitely pulling them over there, but not enough to be actually covalent. This is just about covalent character. So this can the reason I'm talking through this is because this can influence the lattice enthalpy values. It's that difference between the theoretical. If you calculate it theoretically, you don't account for any of this. But experimentally, you'd find, oh, right, very different value from the theoretical. Well, it's because you get this. Well, one reason, anyway. Similarly, if you look at aluminium, but aluminium fluoride, aluminium chloride, aluminium bromide, you've got a similar sort of pattern going down there. The aluminium stays the same, all right, so there's no difference in the charge on that, but I just realised I've got, I've got a different comparison over here for magnesium halides. But the fluoride, chloride, bromide are different sizes. You've got more shells, so you've got bigger ions. And again, you've got this increasing influence on the covalent character, you know, because they're going to get pulled further away. So, this little bit here is quite important, this bit at the top. This is the theoretical bit. Those assumptions that I said we make for the theoretical enthalpies is assuming what is often known as a perfect ionic model. All right, so that, I think that's possibly one of the questions on the assignment. What is meant by the perfect ionic model? This idea of them being 100% ionic, and then here it says spherical. I described that as being the point charge with the charge located right in the centre. That's really what that means. The Born-Haber one, and it makes you wonder, you know, well, why would you bother with a theoretical one? Well, because you don't have to go through all the, you know, atomizing this and ionizing that. So if you've got a compound with some covalent character, you'll get, see, nicked it off somebody else. You can't trust them, can you? If you've got covalent character in the compound, you can pick that up because there's a difference between the theoretical and the calculated Born-Haber experimental enthalpies. The more the covalent character, the bigger the difference. All right, so I can't remember whether I've ever put that into the question, but it's yes, yeah, it should be recording, I hope. As long as the battery doesn't run out in mid-session. This idea of the, you know, what that actually means, it's distorting the ions because of the size of them and that sort of thing. If it's 100% ionic, you have this spherical, you know, layout for the ions. To be honest, sodium chloride's not far off. You get quite good agreement between the theoretical and experimental values for sodium chloride. I think I'm trying to think of the good example. Oh, the aluminium, not aluminium, was it? It was silver chloride. Isn't. If, however, you get the ionic with the covalent character, then you get this distortion where the electrons are pulled across. It's not quite polar covalent, but it's just got that extra pull on the electrons, so that they're coming close, but they're not quite being shared. They're not quite spending time around here like you would in a polar bond, but they are pulled over. So you'll get the difference between the values if there is that sort of type of bonding. We're not going to look at the example on there because that is, we're not quite ready for the idea of a calculation yet. I won't save the changes on there. Now, I have some handouts and questions that will go with this.